Okay, guys, thank you for coming. Sorry I'm a couple minutes late. Hope that everybody's having a good weekend. I'm sure it's a busy one, getting ready for finals. Is this everybody's first final, or you have other finals? Well, first one? First or second one? Okay. Yeah, so we have till Wednesday to get ready for this. So it's kind of nice. We're going to do this review, and then we're going to have a few more days to get ready for the review, or to get ready for the final itself. Don't forget, I'm going to be around the office a lot the next few days, so feel free to stop by if you have some questions. The final will be here at 5 o'clock on Wednesday, and you should bring a calculator. You're allowed to use a calculator. Of course, you've got the review packet. There's some practice problems in the review packet, and also a list of some topics, especially from the last part of the semester, things that were not in the review packet for the 2 midterms. I've got a lot of that in here. There are, again, 5 theorems to learn, of which I'm going to put 4 of them on the final and ask you to prove 2 of them. That's going to be about a quarter of the exam. So that should be, hopefully, easy points to get. When I taught the class last time, 3 years ago, I used a slightly different set of theorems. So if you're taking the sample final that I posted online, you might notice that there's, I think at least one of those theorems might be different than the ones that I'm asking you to learn. So with respect to that part of the final, the sample final isn't necessarily the most helpful thing, perhaps. But you already know what's coming for that part of the studying anyway. If you have any questions about those proofs as you're going through them, what you need to include, what you don't need to include, you can ask me about it. I think I tried to be somewhat clear. For example, in Theorem 13.2, there's also Two's lemma, which is part of Theorem 13.2, and I do want you to learn that. Right, but if there's any other questions like that that you have, I think that the one with the Legendre symbol of 2 with respect to p, there's 4 cases, and I only did 2 of them in class. Right, so what you should do with that is feel free to you can either just say the other cases are similar, because they really are similar. Just focus on the 2 cases that we had done in the class. I think you sent me a question, and I didn't get a chance to write you that. But that was a question as well. If I didn't prove it in class, it really is something similar. You don't need to prove it. You're welcome to use the book's proof or my proofs, or some combination of them. But just make sure that you don't skip a whole section of the proof that you were supposed to include. So check with me if you're not clear on anything as you're getting those ready. But that's something that you can be practicing. Pretty much, I would say every day you should spend a little bit of time just kind of rehearsing those again. Okay, because those are going to be hopefully helping you to get some confidence and get some points on the final. There aren't too many other big important theorems since the last exams. I just have a few things. I guess 6 bullet points here of things from chapters 6, 11, and 13. But that list is pretty comprehensive. You really need to go back to the old review packets to kind of review what was covered on the first 2 midterms. I think I did get blank copies of those first 2 midterms posted for you now. So if you do want to print those out and just practice them again, feel free to do that. Might not be a bad idea. Okay, so that's the main thing. I've also put up, as of last Wednesday or so, I put up another practice quiz. So there's a practice quiz from almost every single week of the semester, as well as quite a few group works. So practicing those group works and practice quizzes, I think, would be another really good thing to do. So there's lots of problems. There's no lack of problems available to study from. So you just have to put the time into it and balance it with your other exams, and hopefully you can juggle it okay and just go back and forth between your different subjects a little bit until we get done with all of this. So, okay, I haven't gotten your last homeworks back yet, the ones that you turned in on Wednesday, but as soon as I get those back, I'm going to be putting those grades in, and then I will drop your lowest homework grade, and I'll have a new updated grade sheet before the final as well. So those are the main things that I can think of. Does anybody have any, I've got a bunch of practice problems, of course, that we're going to work on, but I want to know if anybody has any questions for me, generally speaking, before we get started. Pretty clear where we're at? Okay. All right, well, thank you guys for coming in on a Sunday to do some work. It's just the best day for me, especially to do some of this. So, all right, so let's do some practice problems. I'm going to start over here. And this is just to kind of get us warmed up a little bit and to remember some, I'm going to do some new problems from the recent material, but I'm also going to go back and do some older problems as well, just to remind you of a bunch of things. So here is an example. Let's start with this one as number 1 here. So the question is the following. And by the way, these questions and answers are on my website, so you can always look these up later as well. Old MacDonald sells chickens for $5 each and geese for $8 each. Okay? If he collects $99, how many of each were sold? Okay. So you might be able to just finagle this one by a brute force method. I'm sure with a 2-hour exam you could probably figure out all combinations and sort it out. But I want to go through it procedurally because, of course, sometimes the numbers are bigger and you can't just do things so quickly in your head. So does anybody have a suggestion how we could maybe, what kind of a problem is this? What does this have to do with? Diophantine equations, exactly. This is going to be basically a linear equation that you're looking for integer solutions to, okay? So can somebody help me set up the equation? What would I need to establish here? So we can set up x and y as some variables for the numbers of chickens and geese, right? So let's do that. Let's let x equal the number of chickens. And then I'm going to let y equal the number of geese that were sold. Okay, so then the equation is chickens were $5 each, so that's 5 times the number of chickens, plus 8 times the number of geese. That would have to add up to 99, right? And of course, I'm looking for solutions where x and y are at least 0. It doesn't make sense to find negative solutions to this problem, so we'll only look at positive values of x and y. And x and y, of course, x and y should be integers as well. That goes without saying, right? Do Diophantine equations always have solutions? No. Do you remember the condition that governs whether a Diophantine equation has a solution or not?
The GCD of the two numbers divides
the other side of the equation, right? So in this case, the GCD of 5 and 8, right, has to divide 99. So as long as that's true, then there will be a solution. So in general, the form of the Diophantine equation is ax plus by equals c. And the condition is that the GCD of A and B has to divide C. I think that was the notation that we had used when we covered this. This goes all the way back to the beginning of the semester, just reviewing something kind of on the older side. Okay, so the way that you proceed to solve these things is you express the GCD as a linear combination of the A and the B, right? So that requires the Euclidean algorithm, okay? So we're going to use the Euclidean algorithm here. And these numbers are not so terrible. We won't have to spend that much time to figure this out. Basically, 8 has to be divided into 5. So it goes into 5 one time with a remainder of 3. And then 5 goes in one time into 3 with a remainder of 2. 3 goes one time into 2 with a remainder of 1. And that's your GCD. Okay, so the GCD of 8 and 5 is 1. Okay? So then you just run this algorithm backwards, so to speak. So you start with 1 and you write it as 3 minus 2. And then you take the 2 and you rewrite that as 5 minus 3. I like to simplify as I go along here, so that's 2 times 3, 2 factors of 3, and then with a minus 5 on the end of it. Then I'm going to take the 3 and rewrite that as 8 minus 5, and subtracting another factor of 5 here. And then I'm going to simplify it again. So 2 times 8 minus 3 times 5. Okay, so this is running the algorithm forward and backward. So in other words, the number 1 is equal to, I'm just going to put things in the same order that I see them here. So I'm going to put the 5 first. So 5 times negative 3 plus 8 times 2. So just to put it in the same order so that so for example, one solution here would be negative 3 and 2. Okay. So the first step is to just write the GCD in terms of the A and the B. Okay? Then what you're going to do is scale both sides of the equation through. You're going to scale up to whatever this right-hand side number is, which is 99. So I'm going to multiply through by 99. Multiply through by 99, so that's what I'll have on the left is 99. And when I'm multiplying the 99 through on the other side, I want to preserve the 5 and the 8. So I'm not going to be multiplying the 99 into the 5 and the 8. I'm going to leave those as is. But I'm going to take 99 times negative 3, and I'm going to get negative 297. And I'm going to take 99 times 2, and I'm going to get 198. Okay? So I actually have come up with one solution to my Diophantine equation here. It's not an acceptable solution because we have a negative number as one of the solutions. But we do have a solution which we usually refer to as x naught, y naught. So this would be negative 297, comma 198. Okay? So the trick here is to start off by finding one solution to the equation. Everybody with me so far? Okay? And then we have this formula for getting all of the rest of the solutions. So let me just remind you what the general formula is. This is one that you will want to know. What you can do is you take this x naught and y naught value and you do a little bit of transformations of those two solutions. So the first one is plus b over d times t. And the y naught is with minus a over d times t. Remember that the a and the b are the original coefficients here. A and b. And then the d is just the GCD of those two numbers.
Could we start, when we started, could we have divided the GCD out as it does the problem?
We could have, but see, the GCD was 1.
Right, I know, but then over there it would always be just GT and minus.
Oh, yeah. If you have a problem where the GCD is not 1, so if you have a common factor of all of these terms here, if there is a common factor, you are more than welcome to divide it out before you even start the problem. You will not gain or lose any solutions by doing that. So you can divide the original problem through originally. In other words, take the A and the B to be the result after you've divided through by some common factor that you see in all three coefficients. That way, your D would always be 1. Okay? And then if your D is always 1, you don't have a denominator here. Okay? But this is just the general form that would work in any circumstance. So what we're going to have here is negative 297 plus 8t, comma, 198 minus 5t. Okay? So this is like all solutions to that Diophantine equation. T is just any integer. Okay? So what would I do next? You have to set both of these greater than 0, right? Or greater than or equal to 0, right? You have to have a non-negative solution. So negative 297 plus 8t, that has to be greater than or equal to 0. And the second one, 198 minus 5t, that has to be greater than or equal to 0. Okay? So we have both of those conditions. So coming back over here, So that means that t would be greater than or equal to, I'm going to use the first equation here. I'm going to move the 297 to the other side and then divide by 8. So t is greater than or equal to 297 over 8. And from the second part of it, if I move the 5t to the other side and then divide by 5, t is less than or equal to 198 over 5. Okay. 297 divided by 8 is approximately 37.125. And 198 divided by 5 is 39.6 actually. So there are two different values of t that satisfy both of those. Remember, t needs to be an integer. Okay? So 37 is not included because we already have a decimal after this 37 here. So t would have to be 38, and 39. So we're actually going to get a couple of solutions here. Okay, so if t is equal to 38, let's just see what we come up with. So t equal to 38, we just put that in here for t, and we're going to get x equals 7, y equals 8, I believe. Okay, and if t is equal to 39, we're going to get x is equal to 15, and y is equal to 3. So there's two different solutions that work. You could have 7 chickens, that would raise a total of $35, and 8 geese, which would be $64. 35 plus 64 is 99. Or you could have 15 chickens, so that would be $75 worth of chickens, and then 3 geese at $8 a piece, that's $24 worth of geese. That's also $99. Okay, so there's a couple of different solutions here. Okay, does that make sense to everybody? You comfortable with that? Okay, so I just wanted to review that. Now, some of the Diophantine equation problems that we did had 3 variables in them. You've seen a few examples like that where there are 3 unknowns. But in those cases, we generally had 2 different equations, right? So you could actually take one of those equations to eliminate one of the variables from it. Okay, so that's another scenario. Although you're eliminating a variable, don't forget that once you finally solve the Diophantine equation that you have, not only do the 2 variables that are left in the Diophantine equation need to be non-negative, but when you plug those 2 non-negative values in to solve for the 3rd variable that you had eliminated, well, that 3rd variable perhaps has some constraints on it as well, such as maybe it needs to be positive also. So I think we did a problem with a movie theater, and there was a certain number of proceeds for men, women, and children. So we had 3 variables, the number of men, the number of women, and the number of children. That was a very similar type of thing. You had to have non-negative solutions. You might have eliminated the children from the Diophantine equation, and you might have just been solving for the men and women. However, once you've found acceptable solutions for the men and the women, you would have to plug each of those into the relationship with the number of children and make sure that that was also reasonable. Okay, does everybody know what I'm talking about? Does that make sense? So that's sometimes something that you have to pay attention to. Okay. Everybody good with this example? Just kind of wanted to warm up. Main thing is I just wanted to remind you about this equation here for getting the general solution, the list of all solutions to that Diophantine equation. Okay, let's change gears. Do something different here. So number 2, solve this system. I'm going to give you a system here. The first equation is 10x to the 6th is congruent to 3 mod 13. And the second one is 16x is congruent to 26 mod 50. Okay. So this is a system of congruences. When you're thinking of systems of congruences, what do you often think of? The Chinese remainder theorem. So chances are we're going to be using that. You have to make sure that your mods are pairwise relatively prime. Well, 50 and 13 are relatively prime, so we don't have any trouble there. The 13 is a prime number. That's kind of useful to know, so we could actually maybe take advantage of that. We'll see. Does anybody have a suggestion how to maybe start working on this? It's not really a typical system because there's a 6th power of x in it. Okay, but does anybody see a place that they could start to maybe help us make a little progress? There's several different things we could do here to start with. The 10 and the 16. Try to get those out of the way, in other words. So, 10 in the world of mod 13 is going to be multiplicatively invertible, right? It's going to be possible to cancel it. So we would just need to figure out what an inverse, so for this, I think that's a good idea. For the solution here, what I'm going to do is I'm going to try to find an inverse for 10 modulo 13. How do we do that? How do you find a number that you can cancel the 10 with in mod 13? Yeah, we can use the division algorithm and basically the Euclidean algorithm to do it. Or you could just, with numbers this small, you can just guess the answer. Because, you can see, for example, that 10 times 4. 10 times 4 is 40. But in mod 13, 40 is the same as 1. Right? So essentially, 10 times 4 is 1. That means the 4 is like the inverse for 10. If you can just see it like that, then you'll save yourself the hassle of it. But just so everybody, let's just go through it anyway, just one more time. So if we use the Euclidean algorithm on it, we would just take 13, we would divide by 10, we get a remainder of 3, and we put the 10 here, it goes into 3 times with a remainder of 1. Okay? And then we would work backwards. 1 is equal to 10 minus 3 times 3. And then I'm going to take one of the 3's, not both of them, and back substitute with 13 minus 10 again. And that comes out to, once I simplify it, 4 times 10 minus 3 times 13. Okay, so in mod 13, 4 times 10 is congruent to 1. This is mod 13. Okay, so again, you can always, with bigger numbers, you can work that out just with the Euclidean algorithm. So let's take this top congruence then, and let's multiply it through by 4. Right? But that's going to cancel that 10 for me. So I'll get x to the 6th is congruent to 4 times 3, which is 12, mod 13. 12 is actually the same as negative 1 in mod 13, so if you prefer to write it that way, you can. Okay, let me just leave it like that for now. Let's look at the other congruence. Does 16 have an inverse in mod 50? Can you take 16 and multiply it by something and get 1 in mod 50? No. So how are we going to, does anybody have a suggestion how to address the second congruence? I would suggest, I saw some people suggesting that there's a common factor now in all 3 terms, so let's divide through by that. Okay, so we can divide through by the way, congruences, okay, so this is a linear congruence of the form AX congruent to B mod N. What's the requirement in order for this to have a solution at all? Because sometimes congruences don't have solutions. The GCD of A and N has to divide B, right? You guys remember that? So we just need to be a little careful here. The GCD of 16 and 50, well, that's going to be 2. Okay? And 2 does divide 26. So there is going to be a solution to this congruence. And But the way that you can most easily handle this is just to divide the whole congruence through by 2. Okay, so you can divide this through by 2, put 8, 13, and 25 there. Make sure you divide the mod by 2 as well, not just the coefficients there. So normally you can't do that unless you're doing it to all parts of the equation. Okay? So now in the world of mod 25, 8 will have an inverse. Can somebody tell me what it will be? Negative 3, right? 8 times negative 3 is negative 24, which is the same as 1 in mod 25. So I can take this congruence, and I won't go through the Euclidean algorithm this time. I'm just going to go to the answer. So if I multiply by negative 3, I'll get x congruent to, well, it would be negative 39. But in mod 25, I could replace that with 11 if I wanted. Mod 25. Okay? Everybody with me so far? By the way, so you're going to get one unique solution. Obviously, we got one unique solution for x in mod 25. If we go back to the original congruence, which was mod 50, we would have 2 incongruent solutions mod 50, right? So in mod 25, there's only one solution, which is 11. But if I look at it in mod 50, there would be 2 solutions, which would be 11 and 36. Right? See, 36 and 11 are both solutions here. Because you add 25 to 11, you get another solution. So just be aware of that. You can basically view this as one solution in mod 25, or equivalently, 2 solutions in mod 50. Okay. Everybody with me so far? Okay, so let's just rewrite what we have here. We have x to the 6th congruent to 12 mod 13. And we have x congruent to 11 mod 25. The second congruence is in pretty good shape because it's just a simple setup for the Chinese remainder theorem. Just in this form is exactly how you want it. But the first one is still x to the 6th power. So does somebody have a suggestion how we can proceed to work on the first equation further? X to the 3rd to the squared.
Yes.
So, so you're suggesting we do that. Okay, so we could like write it like that. Okay, so essentially we are saying that for this first, we don't even know for sure if this has a solution yet, but if there's a solution, it's got to be something that's a situation, it would require 12 to be a quadratic residue, basically, is what it would be. In other words, negative 1.
Do we do, oh, sorry, do we do indices? Is that what it is?
Oh, there's a good idea. That's actually what I was going to suggest that we do, is use indices. Whenever you're trying to deal with powers of an unknown variable, it's a good suggestion. But let me finish my thought first. So 12 is the same as negative 1 in the world of mod 13, right? So under what circumstances is negative 1 a quadratic residue? In other words, when is negative 1 a perfect square? Modulo which primes?
1 mod 4.
P has to be congruent to 1 mod 4. Do you guys remember that? The Legendre symbol of negative 1 with respect to P is 1 if and only if P is congruent to 1 mod 4. So, of course, 13 is congruent to 1 mod 4. So that means that negative 1 is a quadratic residue with respect to 13. So there will be something whose square is congruent to 12 here, okay? Whatever that something is, right, then you'll have to see whether that thing can be cube rooted in mod 13 in order to know for sure if you actually have a solution. Okay, so it's not clear that this has a solution yet. But what I'm going to suggest we do instead of using the quadratic residues is I'm going to follow Abir's suggestion here, which is to actually take indices of the equation. So I'm going to do that here. So let's take indices. what do we need to do in order to take an index of something? We need to have a primitive root, don't we? So we need to have a primitive